Welcome to our webinar on introducing Visual MODFLOW Flex version 6. My name is Kristian Doerken. I'm the product manager at Waterloo Hydrogeologic. A few housekeeping rules before we get started. I will be using GoToMeeting. Please mute your microphone or phone lines to eliminate any background noise. Then we'll have a live Q&A session at the end of the presentation. If you think of any questions during the presentation, feel free to jot them down in the chat feature for questions or comments. And at the end, you can always email sales and support if you think of anything else after the fact. And we are recording this webinar, and the recording will be available on our YouTube channel in the next few days. So what we'll be going over in this webinar is a brief overview of Visual MODFLOW Flex, how it works and what it's capable of, and then a summary of the new features and improvements that we have introduced with version 6. Then we'll do a live demo and then have a Q&A at the end. So Visual MODFLOW Flex is a graphical user interface for building conceptual and numerical groundwater flow and transport system models. You can import and interpret and conceptualize a lot of different sources of data. There's a listing right here on the screen. And then you can build your conceptual model, so you would construct your model horizons or your contact points between your hydrogeostratigraphic layers, define the properties for those layers, and then set some boundary conditions. You can do this either conceptually or numerically. In order to build your numerical grid, we have 3 different types of grids that you can work with. So there's the standard rectilinear grids that are in the main family of MODFLOW codes, and the more modern control volume finite difference grids, which we support the Voronoi grid type and the Quadtree grid type, which is new to version 6. Once you've defined your groundwater model, you can simulate flow and transport using any number of engines that are supported in Visual MODFLOW Flex, and then also some of the utilities, including ZoneBudget, particle tracking, and PEST for assisted model calibration. And then there's also some conceptual modeling and visualization tools. So Visual MODFLOW Flex is based on workflows. You have a conceptual model workflow and a numerical model workflow. The former is grid independent and is recommended for new projects and GIS or vector data. If you have a lot of that, then the conceptual model is the way to go. And if you're working with numerical models, the use cases for that would be as if you're importing an existing project or you want to do some final adjustment and calibration to your numerical model. The workflow has a series of steps that get validated as you progress through building your model. Once you're done, you can convert your model into a MODFLOW model or a MODFLOW-USG model, and then proceed to the numerical workflow, again with a series of steps that allow you to define the various portions of your model. The main new features that we've introduced in version 6 are significantly around unstructured grids and improving the functionality for those. So the first thing that we've done is introduced a full workflow for working with unstructured grids that has all of the steps that you're used to when working with finite difference grids. There's the defined modeling objectives, defining properties, boundary conditions, and new is defining observation wells, zone budget zones, and the addition of particles for particle tracking. You can also now build Quadtree grids, and we'll go over that in the demo. You can also now refine vertical layers, and then also the ability to support the ghost node correction package. This is particularly useful for the Quadtree grids, where this package corrects for changes in the flow term based on the assumption cell centroids of your model are perpendicularly bisected between each of the cell centroids in adjacent faces. So the ghost node correction basically introduces these ghost nodes that are located at the perpendicular bisector or where the perpendicular bisector would occur, and then corrects that. So in this example in grid cell 1, you have 3 ghost nodes that then get interpolated back to the cell centroid of grid cell 1. We've also done a fair bit of work around particle tracking, the main feature of which is support for ModPath 3DU, which enables particle tracking for unstructured grids. We've also added some significant capabilities around how you define particles. So you can now define individual groups of particles, each with their own separate release time. You can also have various groups defined based on conceptual elements, and we'll do that in the demo. You can also define particles in the cross-section view of the finite difference grids, and then also set elevations based on conceptual elements such as layers, surfaces, or even a constant value. It should be noted that ModPath 3DU was developed by SS Papadopoulos and Associates, and it's not installed with Flex version 6, but has to be downloaded separately. And you can get a free copy by registering at the SSPA website, and there's a link at the bottom of the screen right here. We've also done some significant improvements around ZoneBudget, the first of which is supporting ZoneBudget for unstructured grids. You can also now use conceptual elements such as points, lines, or polygon features to define your zone budgets. And then if any of these features carry an attribute field that you want to use to define your zone budget zones, say you wanted to look at land use types, you could do something like that where if you had a set of polygons that defined land use and each one had a different or maybe non-unique land use type, then you could aggregate them that way. So you're looking at agriculture and you want to see how much groundwater is discharging to agricultural zones, you could group them based on that land use type. And we'll go over that again in the demo. One of the last major features we've introduced in version 6 is the velocity vector visualization capability. This would be familiar to those of you that are classic users. You'll be able to now visualize velocity vectors or the velocity vector field through the finite difference grid and through the unstructured grids as well. And that's sort of split into two different components. You can see the velocity vectors, and you'll also be able to see the normal velocities as a color map. So this color map shows then flow into and out of the plane, where red is away from you and blue is towards you in this particular view. And I'll go back one slide and highlight that the velocity vectors can be scaled either using the total 3D magnitude, the in-plane magnitude, and also by direction. So all vectors are scaled the same, and you just get to see which direction they're going. You can also scale vectors by average linear velocity or using the Darcy velocity. Other enhancements are the ability to define observation wells in groups, and then we've also done some various improvements to property and boundary condition editing, data import and export formats, and usability and performance enhancements as well. And you can get a complete list of those if you go to Help and Release Notes, and that'll bring up the README page for Flex. We'll just pop that up right here. And so you can see all the various features that we've done. The entire history of our release is available at the README page. Okay, so let's start with the demo. And we're going to be talking about one model and just going over the various features of Flex version 6 using this model as our example. So we've got a fairly simple watershed model with 6 layers, and there's a few pinch outs. So we'll just show you that. And we've developed this conceptually. So if you've worked through your conceptual model workflow, you'll note now that there's a Q-grid button, so you can define a Q-grid, and we'll get to that in a minute. Just want to show you the Voronoi grid that you can now, if you define your grid, you can go to the layer refinement settings and define how your layers are sublayered if you want any sublayer refinement. So I'll cancel out of that. I've already built a grid for us, so we don't need to wait around for that to finish. And we'll go over the Q-grid builder and how you would develop a new Q-grid. So the first thing you'll see in the upper right-hand side is a general grid size form. You can also name your grid. So if we wanted to call this, say, Q-grid 11, you can do that. And then you can define standard, either a number of rows or a number of columns or row heights and widths. So we'll pick a nice round set of numbers. And again, you can refine your layers using sublayer refinement for each of your conceptual layers. And then over here on the left-hand side of the pane, first of all, we'll hit, say we can hit that, and then you hit apply, and then the preview will update so that we'll have 37 by 39 rows and columns. On the right-hand side, or the right-hand half, you've got a preview on the bottom, and then you've got all of the layers that went into building your conceptual model in the top half. You'll note that there are 2 features here for the boundary, and one is labeled area, the other one is boundary. So if you want to do any refining here, you can either refine the entire area or just along the edges. So we'll click refine along the boundary, and you'll notice that then along the edge of the model, we're going to get some refinement. So you can see it's divided, and this is, again, using the Quadtree grid refinement. The definition of the Quadtree is you have sort of a standard rectilinear grid, but then you can subdivide each grid cell both horizontally and vertically to come up with 4 sub-grid cells, hence the name Quadtree. So another feature that you can do is if we have, say, a linear feature that we want to look at and refine, you can specify a threshold area below which the refining will no longer occur and click this Refine to Minimum button. So Flex will then determine the number of refinements that it will take to get down to a grid cell of that specified area. And in this case, we're just refining down 1. And you can also do that, we'll do that for the rivers. You can always change this value, so if we wanted to go down to 5,000 and add another refinement, you can do that, and you'll notice that the count here on the right increases, so you can keep track of which layers have been refined and by how much. Every time you do a refinement, the area will be decreased by a factor of 4. And then we can also, let's say we want to add some significant refinement to our wells. We can go down even further. So then here, if you want to see how well you're doing in terms of refining and how closely you're following the features, you can actually turn some of these layers on. And since this default color for the rivers is kind of dark, what you can do is if it's selected, you can go to Settings, and we'll just change this to a nice light blue. So now you can see that the refinement in this area is relatively good for the rivers. Let's turn on our wells as well. We could go one further. So now you notice we've added one more refinement. And in doing so, what we've done is we've got a fairly large ratio between these very refined cells and the neighbor, which is still at its original grid size. And you'll note that this metric here, the maximum neighbor length ratio, the largest refinement relative to a neighbor in this case is 16. So we've got a fairly large gap. If you wanted to keep that, then you should turn on the ghost node correction package. If you want to avoid using that, which saves you a fair bit of computational effort, you can smooth the grid. So this button right here allows you to do that, and it will pass over the grid, look for those areas where you've got a high adjacency ratio, and refine those grid cells. So you may have to hit this button a few times to get down to a length ratio that you're comfortable with. If you're not happy with what you've added, or what you've added in terms of defining the conceptual model isn't the only bit of the information that you need, say you've got a site or some other thing like that, you've got a feature in here, you can actually select that in the Model Explorer and add that as well. So we've added in our site condition. We could also refine this down to, let's say, 1,000. And then that area also becomes refined. You'll note here at the bottom that there's a counter for the number of cells. So this tells you about how big the model will become. If you over-refine, then you can always hit the reset button, and then you can start over again. So I've already built a grid similar to this, so I'll just hit cancel so we don't have to wait for that to get generated. And we'll skip right ahead to the unstructured grid numerical workflow. So you'll note now we have a modeling objectives page, and here you can specify your model start date, although that comes from the conceptual model, and some of your model defaults, which also again come from your conceptual model. You can define your properties, boundary conditions, and then here, just to highlight that you can introduce various observation wells and how you would do that in terms of groups. If we've got so far 3 observation groups, 1 for each sub-watershed, and we'll add in another one. So here's observation group 4. You can create a new group or append it to an existing one. And then you'll also be able to, we'll just add in 5, which is the lower portion of the water, or sorry, the upper portion of the watershed. There we go. So you can now add those 5 groups, and they're sitting here separately under the observations node of the Model Explorer for Run 9. The next step is defining zone budget zones. So one of the new features then is to be able to assign using a data object. So say we want to look at our sub-watersheds, and we'll use the blue arrow to define the sub-watersheds. And let's go to just define it in layer 6. You can actually, we'll just pick layer 1. And if you have an attribute feature, as I was mentioning, in this case it's going to be watershed ID, you can use that to define unique zones. And if it's based on an integer, then you can also use those integer field values explicitly to define your zones. Click OK. And bear with me a moment, it does take a minute to do for unstructured grids. And as I was mentioning, a good application for this is if you're looking at things like sub-watersheds or land use. These gaps here are actually holes in layer 1 where it pinches out or has been eroded away. So you can see that we've defined the zones pretty quickly using the attributes here, and I'll turn on the sub-watersheds. Let me just change the styles for that. And actually I think it's sitting under the model. Actually it's the thickness, we'll be able to see it a little better. There we go. The zones conform fairly closely to what you've defined. And if you actually use those in generating your grid, those sub-watersheds, then it would actually conform exactly. We can also define particles. So we've got our stream network, some wells, and our site that we're interested in. What you'll be able to do is define your particles, and you can assign those particles using a data object. So the first thing we'll do is maybe look at the site, and let's assign some particles. We can call them particle group site. Since this is a polygon, what this does is it allows you to specify a grid to define the area. So each polygon will be subdivided into a grid, and you can specify a number of rows and columns along which to define those particles. We've got a bit of an aspect ratio in this one, so we can do that. And then we can specify which layers we want to assign it to. So let's put it in the top 3 layers. And you can place those particles either at the top, middle, or bottom of any of the defined layers. And we're going to assign these as propagating forwards in time, starting at the beginning of the simulation, although you could, if you wanted to, start at 100 or any other time that you specify. And then if you're simulating particle tracking in ModPath 3DU, you also have the option to specify an end time as well for your simulation. So we'll click OK, and those particles will get generated. And then you'll see that we've got 3 sets of particles that now fall inside that polygon. I'll just reset the view here and zoom in plan view. So you can see they conform to the grid that we've specified. We'll also assign them based on a linear feature, just so I can show you that. So again, we'll create some new particles. This time we'll put them on the main stem of the river. And with polylines, you can either choose to evenly space your particles along each line segment. So in this case, you would have 10 particles per line segment, or you can specify a spacing. We'll do 500 meters, And in this case, we're going to try a different way of doing it. You can also specify an elevation. So you can grab a conceptual object from the Data Explorer or from your model tree as well, either a constant, so you would just type in a constant value, a surface, a horizon, or a simulated water table. So in this case, we'll just do a surface. We'll pick ground minus 2.5. And then since this is a river that's most likely gaining groundwater, we will simulate it backwards in time. So you can specify that option here and then click OK. And if you have some particles that fall just outside the grid, then you'll get a little warning, but it'll allow you to keep most of them. So you can see now we've generated particles along the river. If your polyline features are 3D, you can also just use the 3D geometry of that polyline. Same thing with points. And last but not least, I'm going to change the vertical exaggeration so we can see the wells. So these thick black lines represent the screens, and that'll be important in a second. I will now assign some particles using a well object. So if you have a well object, you can now use that well object, and particles will be placed around the screens of each of those wells. The way that works is you'll define a circle around the well screen in plan view, and the first part of that is the radius. So let's dial that back a little bit and put in a 100-meter radius and say we want 12 particles along that circle. And then vertically along the screen, you can define how many circles you want or how many stacks of those circles you'd like. If you specify 1, they'll be placed at each screen midpoint. And if you specify 2, you'll end up at the top and the bottom of the screen. And then for 3, it would be the top, middle, and bottom of the screen. So we'll just hit OK, and I'll show you that. So now you can see we've got a cylindrical set of particles that are surrounding the well screens and at the specified radius from it. Again, if we look in plan view and zoom in a bit, the purple squares are the wells themselves, and then these sort of maroon squares are the particles. So then moving on to the next step, you can choose Flow Engine. At the moment we only have one, but we will be supporting others in future releases. And then you can choose to run ZoneBudget and or particle tracking. And let's go to the translate step. So we've introduced the advanced settings so you can individually choose to run or translate supported packages. So this allows you to introduce external packages if you want that were developed elsewhere, or other packages, and I'm just looking for the GNC package, which is right here. So this is one that I mentioned by default. In Voronoi grids, it's turned off because it's generally not needed. And for the Q grids, I believe it's turned on. You may want to turn it off if you don't have steep gradients between your cells or high adjacency ratios, because it can be numerically intensive. If we go back to the single run step and turn on particle tracking, and you'll see that there are some options now for ModPath 3DU. The first set of which are the iFace parameters. These essentially help you specify where the boundary conditions are applied to your model. Any of those boundary conditions that are flagged with a 0 are considered internal sinks, so the flows will be removed or considered to be removed from the middle of the cell. The 2 flag indicates the sides of the model, so things like constant head cells, general head boundary conditions, and flow and head boundary conditions generally have a default value of 2. And then everything else like recharge, evapotranspiration, drains, and other surface water features are given the flag of 6, which applies to the top of the model. This is all well documented in the ModPath 3DU website. And again, if you register there, then you'll have a link to the manual for that. And then there's also per particle group options. So we've got our 3 different particle groups. You can either specify these parameters individually, Or if you do a multi-select by holding down the Shift key, you can select more than one and then specify changes to any of those global properties. Those are shown in bold. You can also choose to run or not run individual or any of the multi-selected particle groups and then change any of these variables. Again, these are quite well documented on the ModPath3DU website. And then you can go and run the model. I've already run a clone of this model or a copy of this model, so we'll go over the outputs. First of all, if we hit apply, you can see all the data. That can be quite busy. So say you just want to look at the heads observations for the watershed 2 set, you can actually subset your observations now based on each one of those individual groups. So you can select one or more, hit apply, and then have various groups turned on and off as you see fit or as you need. This is particularly helpful in calibration to see how well you're doing in particular regions of the model or areas of interest. So for this part of the model, we'll just take a look at the particle tracking. Change the vertical exaggeration a little bit. And maybe we'll turn off the grid so it's not so busy. So we've got our model here. I've shown the river cells just for point of reference. And you can see our site then flows largely to the river, and our wells that we've put in backward tracking particles then don't really capture much. I think there's maybe one or two particles that make it into to that first southernmost well. And then you can also look at the capture zone of this particular stream. So this is pretty useful. Setting this kind of particle propagation up using these conceptual features then is a pretty big step forward in terms of water resources evaluation and capture zone analysis. So that's sort of that for particle tracking. I can also show you, I can find my run here. You can also change the pathline options. So each of these can have tracking markers. You can drop them at regular intervals. In this case, we'll do 365 days. And if we zoom in to the site, you can see then the 365-day or 1 year time markers. Next, we'll look at the velocity vectors. So I've looked at here our Q-grid run, and I'm showing the velocity vectors then in layer 2. I'll show you the settings of how you can set this up, but you're showing both the velocity vector field and the normal velocity. So in this case, the blue color represents flow into the model or downwards. That would be, in this case, recharge. So you can see the recharge field being applied. And then a neat thing here is that you can see where the streams now are gaining groundwater or are losing to the groundwater as well. So these blue areas here are where the streams are discharging flow into the groundwater system, and then these red areas are where the streams are gaining from the groundwater system. I will bring up the settings here so we can have a quick talk about that. So the way to control these settings is in the velocity map node here on the style settings. You can choose to show or not show, and show a legend as well. And then turn the velocity color map on and off. So if I hit apply, that'll go away. I can bring it back. So then you can toggle through and show various layers or rows and columns. What you also can do is these vector fields are based on a virtual grid, so they're interpolated to the grid. In this case, Flex will try and define 29 vectors in the X direction, 29 in the Y, and about 1 in the Z direction. You'll note as you zoom in, it will reinterpolate and show you more vectors, so you can zoom in and see how that field is in more detail, especially in the refined portions of your model. You can change the color of the vector. You can also, if you say turn off your velocity vector color map, you can change the color of the arrows so that then you'll see if they're in the page or out of the page. And then we'll turn that back on. Change this back to black. And then you'll note also that you can toggle between the Darcy velocity and the average linear velocity. Show the vectors as a direction or a projection, and then the magnitude, which is the full magnitude of the 3D vector as opposed to the projection onto the current layer, row, or column. So let's do that. We'll project onto the current layer. And you'll note now our arrows are very, very small. What you can do is then use the scale factor. I think a scale factor of 20 actually works reasonably well for this particular simulation. And if you have a huge distribution between your velocity vector field, you can also change that from a linear scale to a logarithmic scale. So if you've got high contrast K-zones, that might be a place where you would want to use this logarithmic factoring. You'll also notice that you can turn on and off layer, row, and column views of the velocity field. And if we rotate this here, zoom out a little bit, you can see then that we've got 3 slices, one for row, one for layer, one for column. And then you can see the flow field normal to these cross-sectional views. These same visualization settings are available for finite differences as well. And I think that pretty much concludes the major new additions to Flex. So at this time, I'll open it up to questions and answers. Are there any other questions? If not, we can conclude the webinar. And if you have any additional questions, you can always reach out to sales@waterloohydrogeologic.com or support@waterloohydrogeologic.com. Thank you for your time and have a great day.